right, today's lesson is an introduction to logarithms. So short and sweet, it's nothing too complicated. The big idea here is that we've been talking about exponential functions, right? A times b to the x. Logarithms are just the inverse of those functions, right? And remember, inverse is when you just swap the x and the y. So if I swap the x and the y here, the inverse would be x equals b to the y, okay? So that is what a logarithmic function is. It's just a special way to write it. So one way, let's write this down. I should write this in here. So if you have the function y equals b to the x, right, your exponential function, it is the inverse of this log function, y equals log base b to the x. So just write that down and we'll talk about it. So just like I read that last one, the way you read this thing is log base b of x. Log base b of x. So some things to note is that b has to be greater than 0. And hopefully that makes sense, because if I look at what the b represents in the exponential function, right, your growth factor cannot be less than 0. Right, b can't be 1, because if b was 1, it wouldn't be an exponential function. And then x has to be greater than 0. So all the same things are true for your log function. And this is the one thing that will stick around with you for logs, is that you can also write a log in exponential form, right? So if I have log base b of x equals y, it can be written as b to the y equals x. So whenever I do this, I just remember base to raised to the answer equals this thing. So I kind of like do that little loop in my head when I'm rewriting it. And you can see, well, that makes sense, because if this is the inverse of that, when I write it in exponential form, yeah, the y's and the x's are swapped, right? So here, these are equivalent. They're the same thing. One is written in log form and one is written in exponential form. And as you solve problems that have exponents in it, sometimes it will be easier to evaluate them when they're in log form, and sometimes it will be easier to evaluate them when it's in exponential form. So you have to start figuring out which way you want to write it. So let's start with this example where we're evaluating. We're evaluating these 4 logs here. So log base 5 of 125. So we're going to rewrite it in exponential form. So that would be what? So I can say this would equal, well, the base is the base of the exponent, so that's 5. The power is whatever the answer to this thing is. I don't know what the answer to this thing is, so I can just put a question mark, I can put a variable. Equals, do that so we don't have 2 equals, equals whatever the number is inside the log, equals 125. All right, so what is the missing exponent here? Hopefully you can see if that we raise this 5 to the 3rd power, I would have an answer, right? So this is what you're thinking in your head. You're thinking, 5 to what power gives me 125? Well, the answer there is 3. Same thing here. We're thinking 1/4, right, to what power equals 16? What's the answer to this? Well, to get 16, I know it's 4 squared, but I don't want 1/16. I want the 16 on the top. So that means that thing has to equal -2, right? Because then it would bring it to the top. So that's the solution to that one. All right, here we're thinking 3 to what power is going to give me 0? Well, can I raise 3 to any power to get 0? No, because 3 to the 0 is 1. I can't get less than that. So there's no solution to this. So this is undefined. No solution. All right, here I'm thinking 2 to what mystery power is going to give me 2 to the 8th? Well, that's easy. The question mark has to be 8. So all we're doing here is rewriting things from log form into exponential form and finding that missing piece. All right, we're going to add 2 more definitions to our notebook. One is common logs and natural logs, and then after this we'll always be working with them, so it'll just be something that you get used to. So logs can have different bases, right? They can have different b's, different numbers. Like this one had a base of 5, 1/4, 3, and 2. But the most commonly used log is a base of 10, right? Because it's an exponent with a base of 10. And that base becomes implied. So instead of writing log base 10 of 2000, you would just see log 2000, and you're assuming that you know that's a log base of 10. Mathematicians don't write the 10. It's the most common one. And then another common one is called a natural log. So that's when there's a base of e, right? So for example, this would say log base e of 5. So instead of writing log base e, this is called the natural log. So we rewrite this part as just ln, and you know that that's a log of base e. So log base e of 5 is just written as ln of 5. And when you would read that as the natural log of 5. So we're going to evaluate some of these on our calculator. So just so you know where the log button is, if I have to find the log of 900, there's no base here, but remember that's an implied 10. And the reason that's important is because the only log you can find on your calculator is log base 10. So if it's a base of another number, you can't evaluate it. So if I need to find a log base 10 of 900, I would just type that in. And I would put here it's about 2.954. ln is also on there, right? So ln of e. ln, and then where's my e? See e to the x. Here it is. Or is that my letter e? ln, I think this is my letter e. I don't know if it's going to give me an e. No, there it is. So ln of e is just 1. And that's not approximated as 1. So let's go back and think about this, right? So what you've just figured out here is 10 to what number gives me 900? Well, we've just found out that number is about 2.954, right? Here we've said natural log of e. Well, that's just a log with base e. E to what number? E to the first power will give me e. Well, yeah, that makes sense, right? So really what we're finding out here is that if you have a base in the solution, right, your b and your x are the same, your answer is going to always be 1, because what to what power is going to give you itself, the first power, right? And what about this one, the natural log of negative 1.87? So here we're trying to figure out e to what mystery number is going to give me negative 0.187. So what happens when I type that in? Ooh, it says error, non-real answer, quit. So why doesn't that work? Because e to what number is going to give me negative 1.87? Well, if I graph e to the x, if I think of that graph, it is an exponential function that has an asymptote here at y equals 0. So this function can never be negative because it doesn't go below 0. That's why we're not getting an answer. So this is undefined. It's outside of the domain. Not the domain, the range, right? All right, and then sometimes you can solve for x using what you know about logs and exponents. So here it says 25 equals 10 to the x minus 1. I like to work with it in this order, so I'm just going to rewrite it. And now I'm going to write this in log form, because look what happens. It becomes helpful. So log, our base is 10, of 25 equals x minus 1. Right? So this x is just equal to log, I don't need to write the base of 10, that's implied, of 25 plus 1 is going to be x. And now that's helpful because I can find the log of 25 and I can add 1. So x is about 2.398. What about this one? Natural log of 2x plus 3 equals 4. Let's convert it to exponential form. So our base is e. E to the 4th equals 2x plus 3. Okay, I can solve for this. E to the 4th minus 3 equals 2x, which means x equals e to the 4th minus 3 over 2. I can put all that in the calculator. Divided by 2. x is about 25.799. Right, so that's how going between log and exponential form can help you solve different problems. See you next time.